let's get started then. Actually, let's get our derivatives first. So take a second to get all your derivatives, right? And I also suggest factoring everything. What is my first derivative? My first derivative is 3x squared minus 24x. So 3x times x minus 8. And my second derivative, 6x minus 24. Okay, so we have our first two derivatives. So information from f of x. Now we literally just said this about 15 seconds ago. Justin. What does f give us again? What can we get immediately from f?
Asymptotes and stuff like that.
Yeah, asymptotes and stuff like that. You even said and stuff like that, just like Caleb. This must be like a little thing. And stuff like that. Is that what I'm going to see when I ask this on the exam? What does the original function tell you? And stuff like that. So that to be one of the choices. Okay, so what do we get from this function? What does this function tell us for asymptotes? Anyone at all? Vertical asymptotes and horizontal asymptotes. So one or the other or both. Which one do you want to answer? No asymptotes. Thomas, why does this function have no asymptotes? Can you give me a very brief reason?
It's a polynomial.
It's a polynomial. Polynomials do not have vertical or horizontal asymptotes. All done. Now I move on. Now I move on to the first derivative. Okay, so as a few people wrote in chat, the first derivative gives us intervals of increase and decrease. It also gives us local mins and local maxes. Okay, so how do we actually go about finding those things? Does someone want to describe that? How do we actually go about finding the intervals of increase and the local mins and maxes? Set to 0? Would you set it to 0? I don't know what this it is. I've said so many times you guys should not use ambiguous pronouns, yet you insist on using them. Right, find where f prime of x is equal to 0 does not exist, right? To be very precise about what we're setting to 0, because there's a lot of things we can set to 0, right? We're simultaneously talking about 3 different functions here, right? So it's important we're very precise. Set f prime to 0 to find critical points or where it doesn't exist. Okay, and then Thomas says create a number line with the critical points. Okay, so that's completely correct, right? You should really think of the number line as the more fundamental thing. I mean, the critical points end up being your cut points for the number line, but that's almost coincidence. I mean, it's not quite coincidence, but the fundamental thing is really doing a number line, because a number line for f prime of x, something like this, where you look at what is the sine of f prime, something like that, things like that, right, Caleb? Because what you're really doing ultimately is you're really trying to solve 2 inequalities, right? You're trying to solve the inequality f prime greater than 0 and f prime less than 0. And we know that how do you solve such inequalities? You have to find out where does that function equal 0 and where is that function undefined, right? Because that gives you the cut points. That tells you where it's possible for the function to change sign. And it just so happens that that's also the definition of a critical point, where the first derivative, this function, f prime, is equal to 0 or does not exist. But the fundamental thing is you are really looking for that number line. Okay, so take about 2 minutes, 2 or 3 minutes to actually get that number line. once you finish your number line, make sure you can then also extract what are the intervals of increase, the intervals of decrease, local min, and local max. Rachel, you got everything? You think so? Okay, so Rachel, what are the cut points for the number line?
I got 0 and 8.
Okay, 0 and 8, right? Because we just discussed that. Where you set the derivative equal to 0 or see where it doesn't exist. So we get 0 and 8. That was the advantage of factoring everything at the very start of the problem, right? All that algebra is already done for you. So x equals 0, x equals 8. So now let me draw the number line. I'm going to put, okay, so I'm going to note what is the sign of f prime. Okay, so we note our cut points, 0 and 8. Let's also note what our test points are. So let's choose easy test points. So -1, 1, and 9. Those are probably easy test points. Okay. Now, a lot of students always ask me this, oh, where do you plug in these test points? Well, what are you trying to do? You're trying to find out what the sign of f prime is. So what function would you substitute these test points in to find out the sign of f prime? Well, f prime, right? Remember, increase and decrease are really gotten by the sign of f prime. So let's now write down all the tests. So let's say, so here's x equals -1. So first of all, actually, let me write down the f prime of x was 3x times x minus 8. So let's look at f prime of -1, f prime of 1, f prime of 9. Now, this function is simple enough that you could just calculate the numbers, right? F prime of -1 is what? -3 times -9. But you don't really care about the number, right? So you don't need a calculator, you don't need anything like that. You just look at the sign of each factor. So for instance, if I look at the sign of 3x for each of these x values, -1 is negative, and then it switches over to positive. So negative, positive, positive. That's the nice thing about working with linear factors, because you'll know they're just going to be negative, and then they're going to switch to the other one. Oh, they'll start positive and then switch to negative. X minus 8, let's see, that's negative, it's negative, and then it's positive. All right, again, I don't care about the numbers, just the signs. So overall, I get positive, negative, positive. And so I'm going to note that on my chart. The derivative goes positive, negative, positive. So sign charts should be something that you guys are really used to doing, right? From pre-calculus, remember when you would be asked to say solve an inequality, right? Solve this inequality, 3x times x minus 8 less than 0, right? You should be very used to doing that, say, from pre-calculus, hopefully. Now, once you're done with the sign chart, right, then you can actually extract all the useful information, right? We can get increasing, decreasing. So where is f increasing? Where is f decreasing? Actually, you know what? Let me write these things down here. So where is f decreasing? Where is f increasing? Where does f have a local max? And a local min. So for this, let's just do the x values for the local mins and local maxes. I don't really care about the y values right now. Okay. So when I want to ask you, where is f decreasing? So what are you looking for in the sign chart, right? All four of these things, the decreasing, increasing, local min, local max, they all come from the same sign chart. So what are you looking for the decreasing? Negative, right? You're looking where the derivative is negative. So what I like to do is actually on the same sign chart to remind myself, on the top of the sign chart, I also draw what does that mean about the original function f? And so a negative first derivative means that the original function is decreasing. So I draw a little arrow decreasing to the right. And for the positive derivative, I draw a little arrow increasing to the right to remind myself that's where the original function's increasing. Now, the other reason I like to do that is because then you can actually see exactly what the shape of the function is going to be, more or less. I mean, it's not precise yet because we don't have all the other information, but you can kind of see it's just going to be kind of these two humps. There's going to be one hump and then they're going to have a second hump after that. Okay, so now what is the actual answer? What do you actually write down for where is f decreasing? Pretend this is a MyLab thing and I'm not, or it's an auto-graded question. I'm not looking at it. It's just getting auto-graded. I'm never looking at it again. And if you're wrong, too bad. So interesting. We have two answers. So what is the definition? So it'd be very useful if I knew. What is the definition of decreasing? So for instance, if I say f is decreasing on the set A, then what does that mean to say that f is decreasing on a certain set of x values? It's with brackets because the function is 0 when we plug in 0 and 8. It is? I don't think it is. F is 0. So f of 0 is certainly 0, but f of 8 is something like negative, like 250, 243 or something like that, or 256. F of 8 is definitely not 0. I think it's constant at the derivative function. Well, I'm answering questions about the original function f, whereas f decreasing and increasing. I'm not asking where f prime is decreasing and increasing. Jacqueline, you said I think it's constant at 0 and 8. This function is not constant. First of all, it doesn't make sense to say that a function is constant at a point. You can only talk about a function being constant on a certain interval, and this function is not constant on any interval. But again, that's not what I was asking. I'm asking what is the definition of decreasing? F is less than 0? Really? Well, can I have a function that's negative but increasing? F prime is negative. That's the definition of decreasing, meaning there's no notion of decreasing unless the derivative exists and is negative. So if a function is not differentiable, there's no such thing as it being increasing or decreasing. So decreasing is definitely not defined in terms of increase in terms of derivatives rather. Let's see. Simran says something. Simran says f of x2 less than f of x1. I don't know what x2 and x1 are though. If x gets bigger, y gets smaller. Okay, so we're getting close. So I'll give you what the definition is. The definition is if f is decreasing on the set A, then for any, say, A and B, or I'll use what Simran said, x and y, x1 and x2 in A. Now I have to say something about x2 and x1 and x2. Right, Caleb says if x gets bigger, y gets smaller. So I have to say something about this. For any x1 and x2 in A with x1 less than x2. Okay, so now maybe you can finish the rest. So if I'm going to say that f is decreasing on the set A, that means I can pick any two x values. Assume that x1, the thing I'm calling x1, is actually the smaller of the two numbers. Okay. What does it mean for this function to be decreasing then? So x1 is the smaller of the two x values. So what? What has to be true? I think Simran may have had it. The y value of x1 has to be bigger than y value of x2. That's right. The smaller x value should give you a bigger y value, right? Because you told me as x gets bigger, so as x goes from x1 to x2, the y values have to go down. So in other words, f of x1 actually has to be bigger than f of x2. That is the definition of decreasing. That's actually the definition of strictly decreasing, but we won't really have too much opportunity for that. So for instance, a function that actually has a graph like this, that's actually a decreasing function. It's not strictly decreasing, but it is decreasing. Decreasing actually should have a less than or equal sign there, but we will never deal with functions that are constant in these applications, so I don't really care. Okay, so now let's use that definition to figure out, of course, that's not what I wrote. Thank you. So let's use this definition. It's really going to think I wanted a circle. So let's use that highlighted definition to now actually go back to our function. Where is f decreasing? And there were two answers. There was 0, 8, including the endpoints, and there was 0, 8, not including the endpoints. Now, this function does satisfy the definition of decreasing on both of these intervals, right? I mean, if I said, oh, this function is decreasing from 1 to 4, that's also true. But the point is I want the interval to be as inclusive as possible, right? So am I allowed to include the endpoints according to this definition? What do you think? What do you think, Caleb? Are 0 and 8 allowed to be included? If I include 0 and 8, am I contradicting this definition of decreasing or not?
I think you can include it.
Did you say can or cannot?
You can.
You can. So in fact, we can, because decreasing just says if I pick any two x values, the smaller x value must have a bigger y value. So in other words, if I include 0 and 8, the endpoints, if I say x1 equals 0 and say x2 equals 4, is it true that 0 has the smaller y value? Yes. If I were to choose, say, x1 equal to 2 and x2 equal to 8, again, is it true that 2 has the bigger y value? Yes. Right? So 8 should be included. I went through all of that to remind you what the definition was. We have a notion of decreasing and increasing that's independent of derivatives. The theorem about derivatives and increasing actually says the following. It actually says if f prime of x is less than 0 on the open interval AB, then f is decreasing on AB. But the theorem doesn't say anything about what can happen at the endpoints. So if the function is also continuous, it is decreasing. You should include the two endpoints. Okay, now where is this function increasing? And again, write down the answer exactly as you would write it in MyLab or something. Like, how do you think we should format this answer? See a couple people typing. So I see people writing this. -1 and 9 really doesn't, that the -1 and 9 just tells you where you want to graph the function, but the domain of the function goes from -infinity to infinity. Can we include 0 because we already know it's decreasing? Okay, so that's a good question. 0 was already included in the first interval, so can I include it in the second interval? Well, what is the definition of increasing? Definition of increasing is you choose any two x values. The smaller x value has the smaller y value. So yes, 0 and 8 should be included. It doesn't matter that. Remember, you should not care that there's an overlap at the endpoints because, for instance, for one, there's no such thing as decreasing at a point. So if you tell me, oh, this function is decreasing at 0, that makes absolutely no sense. So there is no contradiction. You can't be both decreasing and increasing at 0 because you can't be decreasing or increasing at a point. Now, the other thing I want to talk about is this union symbol. All of you wrote a union symbol, except Margaret. Margaret, did you do that on purpose, or did you actually think the answer was without a union symbol? She's not sure.
I'm not sure yet.
So let's talk about this union symbol. Again, definition of increasing. If you're going to tell me that the function is increasing on this set, that means I can choose any two x values, and the smaller x value always has the smaller y value. Okay, so I'm going to choose x equals 0 and x equals 8. Those two x values are in this set. 0 is less than 8, but f of 0 is 0 and f of 8 is -256. So here you go. So actually the function is not increasing on this set. How do I know that? Because I just chose two x values that were in the set, and the smaller x value actually has the bigger y value. So clearly f is not increasing on that set. So you are not allowed to include the union symbol, right? The function is increasing on this interval, and the function is increasing on this interval separately, but the function is not increasing on the union of the intervals. So it's a comma-separated list of intervals. Sarah asks, how do we know it increases for infinity after 8? Well, if we look at our sign chart, on the interval 8 to infinity, I have a positive derivative. And we know that if I have a positive derivative, the function is increasing on that interval. So all of that discussion has reminded you, or maybe has taught you. So if the function is continuous as well, you have to include the endpoints where the function is continuous. In these increasing, decreasing intervals. And also, you never use a union symbol when talking about increasing and decreasing. It's a list of intervals. Okay. It is not a union of intervals. And you should understand the difference between saying a union of intervals and a list of intervals. Okay. So maybe you'll have to come back later to watch this again. We'll talk about this. We'll keep on revisiting this, why we don't use unions and why we do include these endpoints in the increasing, decreasing. We'll come back to this a lot. And so at some point you'll be an expert at explaining it, right, Caleb? And so if there's an exam question, like why do we not use the union symbol with this, you'll be able to explain it.
Yeah, like and stuff, right?
And things like that, right? Yeah, stuff like that. Okay, so now let's keep on moving on. So first of all, local min and local max. I just want the x value at x equal, we'll get the y value later. So where does this function have a local minimum, if any local minimum? Because the answer might be nowhere. Some functions don't have a local minimum. X equals 8, and the local max is at, we could see x equals 0. So first of all, that's an advantage of doing what I did, kind of drawing this. You can kind of see very easily there's a local min at 8, there's a local max at 0. Very easily. However, let's say you didn't do that. Can someone tell me the analytical reason why we have a local minimum at x equals 8? What feature of this sign chart tells you x equals 8 is a local minimum? What are you looking for specifically? Negative to positive. That's right. If the derivative changes from negative to positive, right, that means the function is decreasing and then increasing. That means it's a local minimum. As long as that's not like a vertical asymptote or something. Obviously, if x equals 8 was a vertical asymptote, there would be no local minimum there, right? Actually, make sure there really is a point there. Same thing for x equals 0. You're looking for that sign change. You want the derivative to change from positive to negative specifically. So how about this? What if I had a sign chart that was like this? Let's say I had 0 and 8 as my cut points, and I had negative, negative, positive. Where is my local max? Oh, sorry, local min, I wrote first. Where is my local min for this hypothetical sign chart? X equals 8, right? Because it goes from decreasing to increasing. So I get a minimum there. Where is my local maximum? Negative infinity. Well, negative infinity is not a number. There's no such thing as saying there's a local maximum at negative infinity. That doesn't make sense. There is no local maximum, right? Because there is no change. It has nothing to do with local either. There's no such thing as saying something happens at negative infinity. You can't say there's a maximum, whether it's local or absolute, at negative infinity. That makes no sense. Because infinity is not a number, right? But there is no local maximum because there is no change in the derivative from positive to negative. So, okay. Cool. Let's keep on going. So we're done with the first derivative. Now let's get the second derivative. So information from the second derivative. Now it's been so long. Can someone remind us? What does the second derivative tell us? We said it before, but I kind of want to make sure we all concavity and points of inflection. Can someone describe to me? So you can you don't have to describe this in precise mathematical words, although you can. What does it mean to say a function is concave up or concave down? What does that mean to you, concavity? I mean, sometimes I think these words students kind of memorize them, but they don't really understand what they mean. Curved, something to do with the curve, right? Let's see. Caleb says like a U shape, up or down, curved upwards, concave up, smiley face. Okay, good. Right. So concave up goes from negative to positive. I don't know what you mean by negative to positive, but everyone is right about it. Concavity essentially describes how the function is curving. So for instance, a function that curves like this is concave up. And then if it starts to curve the other way, we get an inflection point where that curvature changes, and then it starts to concave down. So that's completely correct. That concavity kind of describes the curvature, or which way the curve is bending. Okay, now can someone tell me how we're going to do this? How am I going to find out where's the function concave up, concave down, and where do we have inflection points? How do we do that? Find where equals 0 or does not exist. Where what equals 0 or does not exist, Thomas? Everyone else has saved you. Second derivative, exactly. See, now we see why it's so important to actually have a complete sentence and not use words like it or something like that. I mean, I knew what you meant because we're in the context of second derivative, but let's make sure you know, right? Essentially, what's going to go on here is, I hope everyone realizes, you're actually just going to repeat exactly what you did for the first derivative, just for the second derivative, right? You're going to set the second derivative equal to 0 and see where it does not exist, and then make a sign chart for f double prime, right? It's exactly the same procedure, just you're doing a different function, right? That's the only difference. Jacqueline, did you realize that it's the same thing except just a different function? Yeah, I knew she knew that. Okay, so let's construct a sign chart. Why is it the same procedure? It's because concavity actually is given by the sign of f double prime. So again, you're just solving inequalities. That's really what this boils down to. You're solving where is f double prime positive or negative. Okay, so what was our second derivative? Our second derivative was 6 times x minus 4. Rachel, you told me before about the cut points for f prime. What are the cut points for f double prime?
4.
4, that's it. Do I also put 0 and 8? No, 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 no. You're all saying no. Are you correct? What's the reason? Why are you all saying no? Is this a meme that we all just say no? Yes, we're correct. Yes. Now you're all gonna say yes, 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 yes. We're correct. So Camelia, why is it no? Why are you all correct? Concavity does not change there. That's for the first derivative because those are the critical points for the first derivative because it's from the first derivative and you're now doing the second derivative. Okay, so everything all you guys said is correct, right? The two parts of that problem they're completely separate, right? The cut points you get for the first derivative have nothing to do with the cut points for the second derivative, right? It's a completely different function. Okay, so let's choose easy test points. Let's choose 0 and 5. It's pretty easy. And then I'm going to write down what is the shape of f above that. And here's my scratch work for the test points. F double prime of 0, F double prime of 5. So the 6 is positive for both. And the x minus 4 is negative and then positive. So I get negative positive. What does a negative second derivative tell me? For instance, so on the interval from negative infinity to 4, what am I allowed to conclude about the function? Concave down, right? And so that looks like an upside down mu. And so concave up, U for up, or a smiley face, or whatever you like to remember. I always remember U for up. So the function looks something like that, right? It's concave down and then concave up. Let's move everything up a little bit. And again, notice that you can actually get, again, more or less what the function looks like, right? It looks like down and then up. So we get kind of the same overall shape as we did before, which is good. One thing I want to point out is, remember before we said that x equals 0 was a local maximum, right? So does it make sense that we got a concave down for that interval, right? If you have x equals 0 and you have a local maximum there, and then a local minimum at x equals 8, right? We better get concave down for x equals 0, right? So on that interval that contains x equals 0, we have concave down, right? Because concave down is the only concavity that would be consistent with the local maximum. Notice that at x equals 8, we had a local minimum before. And if I look at my sign chart for f double prime, 8 is included in the second interval where the function's concave up. And that makes sense, right? Concave up, a u, is the only thing that is consistent with the local minimum. So notice that's actually a sanity check. If you had gotten, say, let's say you had gotten the wrong answer. Let's say you had gotten actually concave up and then concave down. You should have realized that that is actually not consistent with what you wrote down earlier for local min and local max. And so then you know that one of the two things has to be wrong, right? So all of these things, even though the functions are all kind of different from each other, they do kind of talk to each other a little bit, right? So there are consistencies. There are some internal consistencies that you should be able to look for. Okay, so now let's write down everything we want. So we have f is concave down on. F is concave up on. And then F has an inflection point. Okay, so we just discussed this. So concave down, negative infinity to 4. And then concave up 4 to infinity. Make sure that you're not looking at the test points. The test points are only to get these signs, negative and positive. Once you're done with those test points, you can kind of ignore them, right? You're only looking at the cut points to determine the endpoints of these intervals. And then there is an inflection point at x equals 4. Can someone remind us analytically, when you're looking for inflection points, what are you looking for specifically? A change in the concavity. Right, okay, good. All right, and now let's actually graph the function. Okay, so since it's been a while, let's recall what was the original function? The original function was x squared times x minus 12, I think. Yes. And I only want to graph this on the interval -1 to 9. So up until now, the interval -1 to 9 was completely irrelevant. But now the interval is relevant because it's going to tell us how I should limit my graph. Justin, you're good? Okay, so let's get, first of all, important points on the graph because I'm going to need those. So let's get x values, y values, and why are they important? So if you go back through all the work, so first of all, -1 is an endpoint, so we're going to include that. 0 was important, 4 was important, 8 was important, and then 9 is important as well. Okay, so what are the y values? So that's just arithmetic that you can do yourself. And let's remind ourselves, why do we care about each of these points? So -1 and 9 are the endpoints. That's the only reason we care about them. 0 was a local max, right? Yes. 4 was an inflection point, and 8 was a local min. So this is just kind of a reminder to myself when I actually graph the function, what kind of features do I have to make sure are present at those points. And then let's also write summary of the shape of f. Okay, so I like to do this with a little box. So all that increasing, decreasing, concavity, concave up, concave down, I want to now summarize it in one nice, neat chart. So what I like to do is I like to draw a little box, and then I mark off all of the cut points. So we had 0, 4, and 8. So first of all, -1 is an endpoint. Then I had 0, I had 4, and I had 8. So let's actually kind of space these out a little bit. Okay. I'm going to do increasing, decreasing on the top row and then concavity on the bottom row. So all we have to do is then just go back to our work. So our work told us that this function is increasing from -infinity to 0, decreasing from 0 to 8, and then increasing from 8 to 9. And then concavity changed at 4. It was concave down here and concave up over here. Now, the reason I like to do that is because of the following. You can actually see what kind of combination you're going to get. So for instance, on the interval from -1 to 0, I have the combination increasing and concave down. That's different from increasing concave up, right? The function actually looks a little bit different. Now, do I ever have increasing concave down again? No. Okay, then I have decreasing concave down, and I never have that combination again. Then I get decreasing concave up. That's the only time I get that combination. And then increasing concave up. So actually this function actually gives us all 4 possible combinations. And so now let's actually graph the thing. So let's zoom out. So let's keep this here. Now your graph does not have to be to scale, but it should have the correct shape. So here's -1, that's 0. 4 is over here. 8 is over here. And 9 is somewhere over there. And then what are my y values? I have -13, -128, -243, and -256. Let's put those points in. -1, -13, 4, -128, 8, -256, and 9, -243. And then also 0, 0. Okay, so I've marked the 5 important points. The -13 could be over there. Okay, now let's write down, let's put on our sketch. I'm going to put the skeleton in. So the increasing and decreasing. So I had increasing. I can actually use the dotted line for this. This is nice. I had increasing. Then we had decreasing, decreasing, and then increasing. So the function more or less looks like this, right? If it were straight lines. But now let's put in all the curvature. Okay, so if I just look at my chart, right, my colored chart there, right, from -1 to 0, I have concave down, so it better be bending downward. And then from 0 to 4, it's again concave down, so it's bending downward. From 4 to 8, it's concave up, so now it actually switches. And then from 8 to 9, it's concave up. And notice how I actually did I did make sure I have horizontal tangent lines. Right. Actually, I think it's better if it's with the dash. There you go. And so that's it. So there's the orange piece, it's the red piece, green piece, oops. That's the blue piece. Let me just highlight these points again. And let me just label them. So local max, inflection point, local min. And then if you want, you can erase, the gray that you drew to write the skeleton and have a nice neat graph, but I'll just keep it in there for pedagogical reasons. And then we can move it over, we can center it, and there's my graph. And that took us about 45 minutes.